They're among the most powerful stars in the universe, burning hotter, brighter, and shorter than almost any other. These are Wolf-Rayet stars. But what makes them so extreme, and why do they matter for the fate of galaxies? Today, we'll uncover the science behind these stellar giants. If you enjoy this journey, please like, subscribe, share, and let us know your thoughts in the comments. Thank you for watching. Now, let's begin. A Wolf-Rayet star is recognized not by its brightness alone, but by the distinctive shape of the light it sends through a spectrograph. In the late 19th century, astronomers in Paris identified several stars in the constellation Cygnus with unusual spectra. Instead of the narrow absorption lines common in most stars, these objects showed very broad and bright emission features. These emission lines were produced by glowing gases in the outer layers of the stars. They stood out as signatures of helium, nitrogen, carbon, and sometimes oxygen in highly ionized states. The broadness of the lines indicated gas moving at extraordinary speeds, thousands of kilometers per second. This pattern of bright, broad emission became the definition of what astronomers call Wolf-Rayet stars. Over time, the class grew as more were discovered, each with the same unusual characteristics. When an astronomer places a prism or diffraction grating in front of a telescope, the starlight is spread into a rainbow. Superimposed on that rainbow are dark lines where atoms absorb light, or bright lines where atoms emit light. In most stars, the absorption lines dominate because gases in the stellar atmosphere absorb specific colors. A Wolf-Rayet star instead shows emission. The lines are not only bright but also wide. Their width arises from the Doppler effect gases moving outward at high velocity, so the emitted light is shifted across a range of wavelengths. This makes the line broader than in a stationary cloud. Thus, the spectrum tells a clear story of a powerful wind leaving the star at immense speeds. The elements revealed in these spectra indicate the star's surface composition. Many Wolf-Rayet stars show lines of ionized helium and nitrogen. These are grouped into what astronomers call nitrogen sequence Wolf-Rayet stars. Others show lines of ionized carbon and oxygen, and these are classified as carbon sequence or oxygen sequence Wolf-Rayet stars. The fact that these elements appear at the surface is unusual. In most stars, the outer layers are dominated by hydrogen. Here the hydrogen appears to be gone or at least diminished, exposing deeper material. The surface therefore offers a direct look at the products of nuclear fusion that occur inside the star. Nitrogen enrichment comes from hydrogen burning through the carbon-nitrogen-oxygen cycle. Carbon and oxygen enrichment come from later stages of helium burning. The spectrum thus acts like a window into the nuclear processes that once occurred deep within the star. The total number of Wolf-Rayet stars in the Milky Way is estimated to be several hundred, though dust obscuration makes the census incomplete. They're usually found in star-forming regions where massive stars are born. Their existence signals an advanced stage of stellar evolution. Only the most massive stars with initial masses greater than 20 times the mass of the Sun can reach the Wolf-Rayet phase. This rarity is why they form only a small fraction of the stars in the galaxy. Yet despite being few, they are important because their winds and radiation influence the surrounding interstellar medium. When considering why the lines are emission rather than absorption, it is helpful to think about the structure of the outer layers. A dense and expanding stellar wind surrounds the star. Photons from the hot interior excite atoms in this wind, and those atoms then emit radiation at characteristic wavelengths. Because the wind is optically thick, it acts almost like a continuous envelope that glows. The emitted light from the wind outshines any absorption from the photosphere below. This explains why the spectrum is dominated by emission lines, which is rare among stars. Observations across different wavelengths strengthen this picture. In the ultraviolet, additional strong emission lines are seen especially from ionized helium and carbon. In the infrared, Wolf-Rayet stars often appear bright because dust formed in their winds glows at longer wavelengths. In the X-ray band, colliding winds in binary systems produce high-energy photons. Each part of the electromagnetic spectrum adds detail to the portrait of these stars, confirming that they are both hot and powerful. The brightness of Wolf-Rayet stars is substantial, often tens of thousands to hundreds of thousands of times that of the Sun. Yet they can be hard to detect visually because interstellar dust absorbs visible light. Spectroscopy is therefore essential. It not only identifies them but also distinguishes between the subtypes. Classification into nitrogen sequence, carbon sequence, and oxygen sequence groups is done by measuring the relative strengths of different emission lines. The classification system is refined further into numerical subtypes indicating temperatures and line ratios. This framework allows astronomers to compare stars across galaxies and environments. It is important to note that the broadness of the lines also reflects turbulence and clumping in the winds. The gas does not flow smoothly like air from a fan. Instead, it forms dense regions and rarefied gaps. This irregularity affects how photons escape and makes interpretation challenging. Determining the true mass loss rate from spectra requires careful modelling. Underestimating or overestimating the effect of clumping can lead to errors in understanding how fast the star sheds its mass. Wolf-Rayet stars are rare in our galaxy, but easier to count in nearby systems with less dust, such as the Magellanic Clouds. Their presence and distribution help test theories of stellar evolution at different metallicities. In the Milky Way, many remain hidden, but surveys using infrared detectors gradually improve the census. Knowing the number and types is essential for linking them to later explosions as supernovae. The definition of the class has expanded since the first discoveries in the 19th century. At first, only a handful of stars with the striking emission features were known. As telescopes improved, hundreds were found. They remain one of the clearest examples of how spectroscopy reveals physics that cannot be seen with the eye alone. The distinctive signature of ionized helium, nitrogen, carbon, or oxygen, broadened by winds of thousands of kilometers per second, sets them apart from every other category of star. In this way, the Wolf-Rayet star is defined not by its location or color, but by its spectrum. Its identity rests in the lines of light that testify to its extreme conditions. From those lines come the first insights into its structure, composition, and evolutionary state. Each emission line is a trace of atoms energized in violent winds, escaping into surrounding space. Each broadening of a line is evidence of the extraordinary speeds at which matter leaves the star. The definition of the class is therefore inseparable from the physics encoded in their light. The spectrum of a Wolf-Rayet star is not only a label for classification, but also a direct record of chemical states and energetic processes in the outer layers of the star. When an astronomer examines the rainbow of light split by a spectrograph, the emission lines appear as sharp peaks standing above the background continuum. Each peak corresponds to a specific transition in an atom or ion. The most prominent lines in nitrogen sequence Wolf-Rayet stars come from ionized helium and nitrogen, while carbon sequence stars reveal strong lines of ionized carbon, and oxygen sequence stars display oxygen in highly ionized forms. These patterns are not random but correspond to the fusion products of different stages of stellar evolution, visible because the original hydrogen-rich outer layers have been stripped away by intense winds. The helium and nitrogen signatures tell us that the star has gone through the phase of hydrogen burning by the carbon-nitrogen-oxygen cycle. This cycle is one of the pathways by which stars convert hydrogen into helium in their cores. As hydrogen is burned, nitrogen accumulates as a byproduct. Once the outer hydrogen-rich shell is lost, nitrogen from the deeper layers becomes exposed at the surface. Thus, a nitrogen sequence Wolf-Rayet star gives astronomers direct evidence of past hydrogen burning and the chemical transformation it left behind. Carbon sequence Wolf-Rayet stars show something different. Here, the helium burning process has already taken place in the core. In this stage, 3 helium nuclei combine to form carbon, and carbon can further capture helium to form oxygen. When winds or binary interactions strip off additional layers, the products of helium burning reach the surface. The resulting spectra display broad and strong lines of carbon and oxygen. An oxygen sequence Wolf-Rayet star is even more advanced, with oxygen features dominating, suggesting exposure of even deeper fusion products. Each type therefore represents not just a classification, but also a moment in the timeline of nuclear burning inside a massive star. The diagnostic power of these spectra is enhanced when combined with models of stellar interiors. A nitrogen sequence star indicates exposure of core regions that once hosted hydrogen burning, while a carbon sequence or oxygen sequence star indicates progression to helium burning or beyond. Thus, the sequence allows astronomers to place individual stars on an evolutionary path without physically probing their interiors. It is one of the rare cases in astrophysics where the surface truly reveals processes that once occurred deep inside. The emission lines themselves also vary in strength, width, and ionization level, and these variations provide a measure of the temperature and density in the wind. For example, the presence of doubly ionized helium requires a certain minimum temperature, while lines of highly ionized oxygen demand even hotter conditions. By analyzing ratios between these lines, astronomers can estimate stellar temperatures that often exceed 25,000 degrees Kelvin and can reach values above 50,000 degrees Kelvin. These are some of the hottest stellar surfaces observed. The strong ionization further confirms that radiation pressure from intense light plays a key role in driving the powerful winds that define these stars. It is important to note that the emission lines are not simple to interpret. The winds are clumped and turbulent, meaning that some regions are dense and bright, while others are thinner and more transparent. This causes line shapes to deviate from simple profiles. Astronomers construct detailed radiative transfer models that simulate how photons move through such complex winds. The goal is to reproduce the observed spectra and thereby infer wind properties such as density, velocity, and overall mass loss rate. Without correcting for clumping, one might overestimate how much mass the star is losing each year. Studies suggest that clumping can reduce the inferred rate by a factor of 2 or 3 compared to smooth wind models. Observationally, the identification of a Wolf-Rayet star often begins with detection of its broad emission features. Once found, detailed spectroscopy across different wavelengths refines the classification. Ultraviolet data are especially useful because many strong transitions of carbon and oxygen lie in that range. Infrared spectroscopy is also valuable, particularly for stars obscured by dust in the Milky Way, where visible light cannot reach us easily. Combined, these tools allow astronomers to build a catalogue of Wolf-Rayet stars in our galaxy and in nearby systems. The chemical features revealed by spectra also connect to the eventual fate of these stars. Nitrogen sequence Wolf-Rayet stars are often interpreted as earlier stages in the Wolf-Rayet phase, while carbon sequence and oxygen sequence stars represent later stages closer to collapse. However, the exact sequence is not always straightforward. Some stars may transition between types as mass loss continues, while binary interactions can alter the progression by stripping the star more rapidly. Nevertheless, the surface abundances observed remain one of the most important clues to where the star stands in its life cycle. The striking visual of emission lines rising above the continuum carries deeper meaning. Each photon in those lines originated when an atom in the wind was excited and then released its energy. The broadening shows the extreme motion of the gas, a direct sign of outflowing material. Thus, a spectrum is both a chemical map and a dynamic measurement. It shows not only what the star is made of, but also how its outer layers are behaving at the present time. For Wolf-Rayet stars, the spectrum is inseparable from the winds that create it. These winds are among the strongest known for any type of star. Mass loss rates are measured at around 1/1,000,000th of a solar mass per year, which may seem small, but over several 100,000 years amounts to several solar masses shed into space. For a star that began life with perhaps 40 solar masses, this loss dramatically reshapes its evolution. The spectral lines are therefore more than identifiers. They are evidence of a fundamental process that governs the star's future. An additional feature in many spectra is the relative absence or weakness of hydrogen lines. In typical massive stars, hydrogen lines such as the Balmer series dominate the visible spectrum. In Wolf-Rayet stars, the disappearance of these lines confirms that the hydrogen envelope has been removed or reduced. This absence, together with the presence of helium-nitrogen-carbon or oxygen lines, marks the transition from an ordinary massive star to the stripped core object we call a Wolf-Rayet star. As astronomers gather spectra of Wolf-Rayet stars in different environments, they can compare how metallicity affects line strengths. In galaxies with lower heavy element content, such as the Small Magellanic Cloud, the winds are weaker because radiation has fewer atomic lines to push against. This changes the surface exposure rate and can alter how quickly a star progresses through nitrogen sequence, carbon sequence, and oxygen sequence phases. In this way, the spectra of Wolf-Rayet stars provide not only individual insights, but also population-level information about stellar evolution across the universe. In summary, the spectral signatures of Wolf-Rayet stars serve as precise markers of nuclear history, surface conditions, and wind dynamics. The emission lines tell of ionization states, temperatures, and velocities. Their composition reveals which burning products have risen to the surface. Their broadness conveys the speed of the outflow. By reading these lines, astronomers reconstruct the otherwise hidden story of matter, processed in a stellar furnace, and then carried outward into space. The study of these signatures remains central to understanding the nature and progression of Wolf-Rayet stars. The journey of a Wolf-Rayet star begins with a star of exceptional mass far greater than that of the Sun. These progenitors are massive O-type stars, the hottest and most luminous stars known, with initial masses often exceeding 20 times that of the Sun, and sometimes reaching more than 100 solar masses. Their surfaces burn at temperatures of tens of thousands of degrees, and their brilliance outshines the Sun by hundreds of thousands of times. These stars live short lives measured not in billions of years like the Sun, but in only a few million years. From the moment of their birth in giant molecular clouds, they are already fated to follow a path that can end in the Wolf-Rayet stage. The core of such a star is a cauldron of fusion. Hydrogen fuses into helium through the carbon-nitrogen-oxygen cycle, a process that dominates at the high temperatures found in very massive stars. The energy released in this cycle sustains the star against gravitational collapse, but it also produces a radiation pressure so intense that it continuously pushes against the outer layers. This combination of extreme radiation and strong stellar winds gradually strips material away, weakening the hydrogen-rich outer envelope and revealing deeper layers beneath. As the hydrogen supply in the core runs low, the star contracts slightly and heats, further igniting helium fusion. This inner progression sets the stage for the eventual appearance of nitrogen, carbon, and oxygen at the surface. Not every O-type star becomes a Wolf-Rayet star. The key lies in mass and energy balance. For the heaviest stars, winds are so strong that they remove large amounts of mass during the short main sequence lifetime. In some cases, binary interactions accelerate this removal by siphoning material to a companion star. The result in either scenario is that the outer hydrogen envelope is stripped before the star has exhausted all of its fuel. When the fusion products of the core begin to appear at the surface, the star is recognized as a Wolf-Rayet star. This transformation is not a sudden event but a gradual exposure driven by continuous loss of mass. The process of mass loss through winds begins early, even while the star is still burning hydrogen in its core. Line-driven winds propelled by radiation pressure on metal ions carry matter away at speeds of thousands of kilometers per second. Over time, this peeling away of the outer layers exposes nuclear burning products that would otherwise remain hidden. When nitrogen-enriched material becomes visible, this star is classified as a nitrogen sequence Wolf-Rayet star. If mass loss continues further, carbon and oxygen are revealed, leading to carbon sequence or oxygen sequence Wolf-Rayet stars. Each stage represents the star's progress along its evolutionary track. In regions such as the Carina Nebula, the Tarantula Nebula, and other massive star-forming complexes, O-type stars are born in clusters. Observations reveal that many of these stars evolve quickly toward the Wolf-Rayet phase. The most massive examples, sometimes exceeding 50 solar masses, may enter this phase in less than 3 million years. Their evolution is so rapid that within the span of human civilization, a single massive star might proceed through several nuclear burning stages. This short timescale is why Wolf-Rayet stars are rare. Only stars with the greatest initial mass formed in specific environments survive long enough to show the defining emission line spectra. A clear example of this evolutionary connection is seen in the star system known as R136 in the Large Magellanic Cloud. This cluster contains some of the most massive stars ever observed, with masses greater than 100 solar masses. Among them are several Wolf-Rayet stars whose spectra show the processed material from their cores. Their presence in such a young cluster, only a few million years old, demonstrates how quickly massive O-type stars evolve into Wolf-Rayet stars. The combination of high initial mass and intense winds drives the transition on a timescale that is short compared with most astronomical phenomena. Stellar models predict that the exact pathway to the Wolf-Rayet stage depends on both mass and metallicity. In galaxies with higher metallicity, winds are stronger because radiation has more atomic lines to push against. This allows the hydrogen envelope to be stripped away more efficiently, creating more Wolf-Rayet stars. In lower metallicity environments, winds are weaker, and only the most massive stars are able to lose enough material to reach the Wolf-Rayet stage. Thus, the frequency of Wolf-Rayet stars varies across galaxies. The Milky Way, with its moderate metallicity, contains several hundred confirmed Wolf-Rayet stars, while the large and small Magellanic Clouds, which have lower metallicity, contain fewer. Binary interactions provide an alternate pathway. Many massive stars exist in close pairs where their outer layers can be stripped not by winds alone, but also by gravitational interactions with a companion. In such cases, even stars with somewhat lower mass can be forced into the Wolf-Rayet state. The companion may accrete material altering its own evolution, while the stripped star displays the emission line features of a Wolf-Rayet spectrum. Observations suggest that more than half of all massive stars are in binaries, which means that binary stripping is a significant contributor to the Wolf-Rayet population. This dual pathway winds for very massive single stars, and mass transfer in binaries explains the presence of Wolf-Rayet stars across different environments. The transformation from O-type progenitor to Wolf-Rayet star is therefore a story of mass removal. What begins as a hot luminous star with a hydrogen-rich surface becomes, through winds and interactions, a stripped object whose surface directly reflects its core chemistry. Each stage of this progression can be read in the spectrum. Nitrogen signals the products of hydrogen burning, while carbon and oxygen show helium burning. The sequence of spectral types traces the path of stellar evolution in real time. Astronomers use these evolutionary links to build models that connect the early stages of massive stars to their final explosions as supernovae. A Wolf-Rayet star is considered a prime candidate to produce a stripped envelope supernova of type Ib or type Ik. The lack of hydrogen and sometimes helium in the spectrum of these explosions matches the surface composition of Wolf-Rayet stars. Thus, studying the transition from O-type progenitor to Wolf-Rayet star is not only about classification, but also about predicting the terminal stages of massive stellar life. The observational evidence for this pathway is strong, but still leaves open questions. Not all O-type stars that are massive enough seem to become Wolf-Rayet stars. Some may collapse directly without shedding enough mass to show the Wolf-Rayet spectrum. Others may be hidden in dense regions where dust obscures their light. Ongoing surveys in infrared and radio wavelengths aim to uncover more examples and clarify the statistics. Nevertheless, the established picture holds that Wolf-Rayet stars represent an advanced evolutionary stage of the most massive stars born as O-type giants, whose lives are shaped by radiation-driven mass loss. From their birth in molecular clouds to their emergence as hydrogen-stripped giants, these stars demonstrate the extremes of stellar evolution. Their spectra record the journey from ordinary fusion in the core to the exposure of nuclear ashes on the surface. The pathway from massive O-type progenitor to Wolf-Rayet star is a sequence defined by mass metallicity, and sometimes by the presence of a companion. It is a story written in stellar winds, and revealed in emission lines showing how the heavier stars in the universe evolve in ways that lesser stars cannot. The exposure of nuclear ashes on the surfaces of Wolf-Rayet stars is made possible by the steady and relentless removal of their outer envelopes. This process, called envelope stripping, occurs because of the interaction between nuclear burning deep in the core and the outward pressure of radiation acting on the star's layers. In very massive stars, the energy released through fusion is so great that it drives powerful stellar winds capable of carrying away substantial amounts of material. As hydrogen-rich layers are expelled, the deeper previously hidden products of nuclear fusion gradually come into view. This is the physical mechanism that turns a luminous O-type star into a Wolf-Rayet star, whose spectrum shows nitrogen, carbon, or oxygen instead of hydrogen. The sequence begins with hydrogen burning in the core through the carbon-nitrogen-oxygen cycle. The byproducts of this cycle are mainly helium and nitrogen. Normally, these products remain trapped beneath a thick hydrogen shell, invisible to outside observers. In a massive star, however, radiation-driven winds erode the surface, thinning the outer layers, until parts of the nitrogen-enriched material become exposed. At this point, the star shows the characteristics of a nitrogen sequence Wolf-Rayet star. With further evolution, the core contracts and heats, igniting helium burning. Helium nuclei combine to form carbon, and in some cases carbon fuses further to form oxygen. If the winds or binary mass transfer strip away even more material, the carbon and oxygen-rich layers are revealed. The star then becomes a carbon sequence or oxygen sequence Wolf-Rayet star. The stripping process is not a simple peeling away of a uniform shell. It is dynamic, uneven, and turbulent. Stellar winds are clumped, meaning that dense pockets of gas form in the outflow, while other regions remain more rarefied. These clumps alter how radiation escapes and affect how efficiently material is lost. Clumping introduces uncertainty in measurements of mass loss rates, which are derived from line strengths in the spectra. If clumping is ignored, the calculated mass loss rate can be overestimated. When models include clumping, the actual rate of mass loss may be 2 or 3 times lower than previously thought. This correction is crucial because the total amount of material stripped determines whether a star fully reveals its inner fusion products, or whether some hydrogen remains on the surface until the final collapse. Envelope stripping is influenced by more than just winds. Rotation can play a role because centrifugal force at high rotation speeds reduces the gravitational binding of the surface layers, making them easier to remove. Rotation also mixes material between the core and the surface, potentially bringing fusion products to the surface more quickly. In rapidly rotating stars, this mixing can blur the distinction between phases, as nitrogen or carbon may appear at the surface earlier than expected. Magnetic fields, when present, can channel winds along specific directions, modifying how matter is lost. Together, these factors make the process of envelope stripping complex and highly dependent on individual stellar properties. In binary systems, envelope stripping can be dramatically accelerated. If a massive star fills its Roche-lobe material, flows onto its companion through gravitational interaction. This transfer strips away the hydrogen envelope far more efficiently than winds alone. Observations of close binaries confirm that many Wolf-Rayet stars exist in such systems, where the presence of a massive companion has played a direct role in removing the outer layers. In some cases, the companion itself becomes enshrouded in the accreted material, creating additional observational signatures. This binary stripping pathway means that stars of somewhat lower initial mass than the single-star threshold of 20 solar masses can still evolve into Wolf-Rayet stars if they have the right partner. The timescales involved in envelope stripping are short by stellar standards. In less than a few million years, an O-type star can lose several solar masses of material. Mass loss rates for Wolf-Rayet stars are estimated at about 1/1,000,000th of a solar mass per year, but because these stars are so short-lived, the cumulative loss is enough to peel away many solar masses over their brief lifetimes. This rapid loss alters the star's structure and evolution, influencing its path toward eventual collapse. Evidence for envelope stripping is preserved in circumstellar nebulae surrounding some Wolf-Rayet stars. These nebulae consist of material expelled from the star during earlier stages, now glowing under the influence of the intense ultraviolet radiation. The kinematics of these shells measured through Doppler shifts show expansion velocities consistent with stellar winds. Their chemical composition often matches the processed material seen in the star's spectrum, confirming that the surface and the nebula share the same nuclear history. Such nebulae serve as fossil records of the stripping process, capturing layers of ejected matter that once formed part of the star's envelope. The efficiency of stripping is also tied to metallicity, the abundance of heavy elements in the star's environment. Higher metallicity increases the opacity of the stellar atmosphere, giving radiation more lines to push against. This enhances the strength of winds and accelerates the removal of outer layers. In low metallicity environments, such as the Small Magellanic Cloud, winds are weaker, so envelope stripping proceeds more slowly. Only the most massive stars in such environments can lose enough mass to reveal nitrogen, carbon, or oxygen at the surface. This dependence explains why Wolf-Rayet stars are less common in galaxies with low metallicity compared to those with higher metallicity. Observations across the electromagnetic spectrum provide confirmation of these processes. Ultraviolet spectra reveal the strong resonance lines of ions accelerated in the winds. Optical spectra display the broad emission features that define the Wolf-Rayet class. Infrared data sometimes reveal warm dust which can form in colliding winds and condense from expelled material. Radio observations detect free emission from ionized gas in the winds, giving independent estimates of mass loss rates. Each wavelength range contributes a piece of evidence for the stripping process and its impact on the star's surface. The role of envelope stripping in stellar evolution is fundamental because it determines how massive stars end their lives. A star that loses most of its hydrogen envelope before collapse may produce a type Ib supernova, which shows helium but no hydrogen in its spectrum. If both hydrogen and helium are stripped away, the explosion may be classified as a type X supernova. Both outcomes are linked to Wolf-Rayet progenitors. Understanding envelope stripping therefore has implications not only for stellar classification, but also for predicting the types of supernovae that enrich the interstellar medium with heavy elements. Despite decades of study, uncertainties remain in the details of stripping. The exact efficiency of line-driven winds under different conditions, the influence of rotation and magnetic fields, and the frequency of binary interactions all complicate predictions. Observations continue to refine models, but the variability among individual stars makes it difficult to establish a single universal picture. Nevertheless, the broad outline is clear. Envelope stripping is the defining mechanism that exposes the inner workings of massive stars and creates the Wolf-Rayet class. The process can be seen as the unveiling of nuclear history. Each stripped layer reveals deeper products of fusion progressing from hydrogen-burning ashes, rich in nitrogen, to helium-burning products rich in carbon and oxygen. By the time the star is fully revealed as an oxygen sequence Wolf-Rayet star, it is showing the material that once lay at the heart of a blazing stellar furnace. This exposure is not decorative but physical evidence of the extreme forces acting within. The envelope stripping process is thus the bridge between the hidden nuclear core and the visible spectrum that astronomers record. The classification of Wolf-Rayet stars into nitrogen sequence, carbon sequence, and oxygen sequence categories is more than a matter of cataloguing. It is a way of tracing the nuclear stages of very massive stars by observing what is visible at their surfaces. Each category tells a different story about what fusion products have been brought outward by winds or binary stripping. The nitrogen sequence group shows the imprint of hydrogen burning, the carbon sequence group reveals helium burning, and the oxygen sequence group points to more advanced nuclear stages. Together they create a framework that astronomers use to connect observed spectra with theoretical models of stellar evolution. Nitrogen sequence Wolf-Rayet stars are characterized by the strong presence of ionized helium and nitrogen lines in their spectra. The nitrogen enrichment is a direct consequence of the carbon-nitrogen-oxygen cycle, which converts hydrogen into helium in the stellar core. As this process proceeds, nitrogen accumulates as an intermediate product. Normally, this nitrogen would remain buried beneath the star's hydrogen envelope, but in Wolf-Rayet stars the envelope has been stripped away. Thus, the surface directly displays the ashes of hydrogen fusion. The absence or weakness of hydrogen lines in the spectra further confirms that the outer hydrogen layers are mostly gone. These stars are often interpreted as being at the earlier phase of the Wolf-Rayet stage when the products of hydrogen burning are most visible. Carbon sequence Wolf-Rayet stars show a different surface composition. Here, the helium-burning stage in the core has been reached where 3 helium nuclei combine to form carbon in what is known as the triple alpha process. Additional reactions allow carbon to fuse with helium to create oxygen. When winds strip away more of the envelope, these deeper products appear at the surface. The spectra of these stars are dominated by strong carbon and oxygen emission lines, while nitrogen features are weaker or absent. The exposure of carbon and oxygen indicates that the star has progressed further in its evolution beyond hydrogen burning and is revealing the ashes of helium burning. Oxygen sequence Wolf-Rayet stars are the rarest of all, and their spectra are dominated by highly ionized oxygen. These stars are thought to represent a very advanced stage of nuclear evolution, where layers deep within the star rich in oxygen have become exposed. The number of known oxygen sequence Wolf-Rayet stars is small, but their presence confirms that some stars evolve to the point where even the products of carbon fusion are displayed at the surface. These stars are extremely hot with surface temperatures exceeding 50,000 degrees Kelvin, and they demonstrate how far envelope stripping can progress in the most massive stars. The sequence from nitrogen to carbon to oxygen is not always a simple chronological path. but it provides a general outline. A nitrogen sequence star can evolve into a carbon sequence star as mass loss continues, and in very rare cases a carbon sequence star may evolve into an oxygen sequence star. Binary interactions can complicate this progression either by stripping layers more rapidly or by altering mixing processes inside the star. Despite these complications, the classification remains valuable because it connects observable spectral features to the physical processes occurring inside. The temperature differences among the three categories are also important. Nitrogen sequence Wolf-Rayet stars typically have surface temperatures in the range of 30 to 50,000 degrees Kelvin. Carbon sequence stars are hotter, often between 40 and 60,000 degrees Kelvin. Oxygen sequence stars can reach even higher, sometimes over 70,000 degrees Kelvin. These temperatures are far above those of most ordinary stars, and they influence the ionization levels seen in the spectra. The higher the temperature, the more highly ionized the observed elements become, which is why oxygen sequence Wolf-Rayet stars show features of highly ionized oxygen that cannot form in cooler conditions. The classification scheme is refined further by numerical subtypes which indicate the relative strengths of different emission lines. For example, nitrogen sequence stars can be divided into early and late subtypes, depending on whether lines of higher ionization states dominate. This system allows astronomers to rank stars within each category, providing a more detailed picture of temperature ionization and chemical abundances. The refinement is useful for comparing stars across different galaxies, since environments of different metallicity affect winds and therefore the exposure of fusion products. The distinction between nitrogen, carbon and oxygen groups also helps in connecting Wolf-Rayet stars to their eventual fate as supernovae. Nitrogen sequence stars, which still retain helium at the surface, are considered likely progenitors of type Ib supernovae, which show helium lines in their spectra but no hydrogen. Carbon sequence and oxygen sequence stars which have lost both hydrogen and helium layers are thought to be progenitors of type Ich supernovae, which lack both hydrogen and helium lines. Thus, classification is not only descriptive but predictive, linking surface abundances to explosion outcomes. Observations of Wolf-Rayet stars in the Milky Way and nearby galaxies confirm the usefulness of the classification. In the Large Magellanic Cloud, with its lower metallicity, nitrogen sequence stars are relatively more common because weaker winds make it harder for stars to reach the carbon and oxygen sequence stages. In the Milky Way, where metallicity is higher, a larger fraction of carbon sequence stars is observed. Oxygen sequence stars remain rare everywhere, reflecting both the extreme conditions required and the brevity of this phase. Population studies show that metallicity influences the balance among the three groups, providing important tests of theoretical models. The spectral classification also highlights how surface composition reflects processes in the interior. By comparing observed abundances with predictions from stellar evolution models, astronomers test their understanding of how mixing convection and mass loss operate. For instance, the exact nitrogen to helium ratio in nitrogen sequence stars can reveal whether material from deep inside has been efficiently dredged to the surface. Similarly, the strength of carbon lines in carbon sequence stars can indicate how long helium burning has been underway and how completely the star has lost its envelope. These comparisons refine models of how massive stars evolve and how they enrich their environments with heavy elements. An important point in this classification system is that it is grounded in direct observation. The broad emission lines that define Wolf-Rayet spectra are measurable with telescopes across the world and in space. Unlike some aspects of stellar interiors, which must be inferred indirectly, the spectral features of Wolf-Rayet stars are directly visible. This makes them reliable markers of evolutionary state. The nitrogen, carbon and oxygen signatures are unambiguous, and their interpretation as nuclear ashes is supported by decades of theoretical and observational work. The classification into nitrogen sequence, carbon sequence, and oxygen sequence Wolf-Rayet stars therefore serves as a bridge between observation and theory. It provides astronomers with a way to connect surface features to the hidden processes of stellar evolution. It also allows for comparisons across environments, giving insights into how metallicity and binarity shape stellar outcomes. Most importantly, it links present observations to future events, since the type of supernova expected depends on which sequence a Wolf-Rayet star belongs to. In the quiet light of their emission lines, Wolf-Rayet stars reveal both their past and their future. Nitrogen points to the history of hydrogen burning carbon and oxygen to the deeper fusion that followed. Their classification is not arbitrary, but reflects the story written in their cores and carried outward by winds. The nitrogen sequence, carbon sequence, and oxygen sequence groups together form a progression that shows how extreme mass loss unveils the layers of nuclear history one by one, until only the deepest products remain. One of the most defining characteristics of Wolf-Rayet stars is the presence of their extraordinarily powerful stellar winds, which dominate not only their own appearance, but also their influence on the surrounding interstellar medium. These winds are driven by radiation which in such luminous stars is capable of exerting enough force on atoms and ions to push them outward against the pull of gravity. In most stars, the outer layers are held tightly by gravity and winds are weak. In Wolf-Rayet stars, however, the outward pressure of light is so strong that entire layers of the star's atmosphere are carried away into space. This process creates mass loss rates far greater than those of ordinary stars and produces winds with velocities that can reach several thousand kilometers per second. The physics of these winds lies in the interaction between photons and atoms. When a photon from the star's intense radiation field encounters an ion in the stellar atmosphere, it can be absorbed if its energy matches a specific transition in that ion. The absorption transfers momentum from the photon to the ion, pushing it outward. Because the star emits countless photons every second, and because its luminosity is millions of times that of the Sun, the cumulative effect creates a powerful outward acceleration. This mechanism is called line-driven acceleration, because it relies on the absorption of radiation in the spectral lines of atoms and ions. The process is especially effective when many different ions with many absorption lines are present, giving radiation numerous opportunities to deposit momentum into the gas. The velocities of Wolf-Rayet winds are among the highest measured for any kind of star. Terminal wind speeds are typically in the range of 1,000 to 3,000 km per second. Such speeds are deduced from the broadening of emission lines in the spectrum which reveal the Doppler shifts of gas moving away from the star. The width of the lines is therefore a direct measure of the outflow velocity. These values are an order of magnitude greater than the solar wind, which has a speed of only a few hundred kilometers per second. The difference illustrates the extreme conditions that prevail in Wolf-Rayet stars. Mass loss rates are also extreme. While the Sun loses material at a rate of about 1/10 billionth of a solar mass per year, Wolf-Rayet stars lose on the order of 1/millionth of a solar mass per year. Over the course of a few 100,000 years, this loss can amount to several solar masses. Such enormous losses dramatically alter the structure and future of the star. Without them, the star would never expose the products of fusion at its surface, and it would not follow the pathway that leads to a stripped envelope supernova. The winds are not smooth flows of gas, but are instead structured and clumpy. Evidence for clumping comes from the shapes of spectral lines, variability in line strengths, and direct imaging of nearby Wolf-Rayet nebulae. Clumping means that some parts of the wind are denser than others, with overdense regions carrying much of the mass while underdense regions contribute less. This structure affects how light interacts with the wind, which in turn affects how astronomers interpret spectra. If clumping is ignored, mass loss rates can be significantly overestimated because the dense clumps emit more strongly than a uniform wind would. Incorporating clumping into models reduces the inferred mass loss rates, but also complicates the physics of wind acceleration. The dependence of winds on metallicity is another important factor. Metals in astrophysics refer to all elements heavier than helium. These elements provide the spectral lines that absorb photons and drive the wind. In environments with higher metallicity, such as the inner regions of the Milky Way, winds are stronger, because more lines are available for radiation to act upon. In environments with lower metallicity, such as the small Magellanic Cloud, winds are weaker. This metallicity dependence explains why Wolf-Rayet stars are more common in galaxies with higher heavy element content. It also means that the evolution of massive stars is different in the early universe, when metallicity was lower compared to the present-day universe. Observations of Wolf-Rayet winds across different wavelengths confirm these properties. In the ultraviolet resonance lines of ions such as carbon, nitrogen, and silicon show characteristic P Cygni profiles, with absorption on the blue side of the line and emission on the red side. These profiles reveal the presence of outflows and provide direct measures of velocity. In the radio band, free emission from ionized gas provides independent estimates of mass loss rates. Infrared observations sometimes reveal dust formed in colliding winds, which is another signature of strong outflows. Together, these multi-wavelength observations build a consistent picture of winds that are fast, dense, and structured. The winds of Wolf-Rayet stars have important consequences beyond the stars themselves. By injecting momentum and energy into the surrounding medium, they shape the structure of nearby gas clouds. They can create cavities, sweep up shells, and trigger new star formation by compressing molecular gas. The winds also enrich the interstellar medium with processed material from the star's interior. Nitrogen, carbon, and oxygen expelled in the winds eventually mix with the gas between the stars, altering its composition and contributing to the chemical evolution of galaxies. In this way, Wolf-Rayet winds are not isolated phenomena, but part of the broader cycle of matter in the cosmos. The interaction between winds and companions in binary systems adds another layer of complexity. When two massive stars orbit close to each other, their winds can collide at supersonic speeds, creating shock fronts that produce X-ray emission. These colliding wind binaries provide natural laboratories for studying shock physics under extreme conditions. They also reveal the density and velocity of winds more directly than single-star systems can. The geometry of the interaction depends on the balance between the two winds, and the resulting structures can sometimes be imaged as curved arcs of emission. These systems are therefore valuable for testing theories of line-driven winds. The study of Wolf-Rayet winds continues to refine models of stellar evolution. Accurate mass loss rates are critical for predicting the lifetimes and end states of massive stars. If the winds are stronger than expected, a star may lose enough mass to avoid direct collapse into a black hole, instead producing a supernova. If the winds are weaker, the star may retain more mass and collapse directly. The role of clumping, metallicity, and binarity all contribute to this uncertainty. Nevertheless, the consensus remains that strong winds are a defining feature of Wolf-Rayet stars and a key driver of their evolution. It is important to emphasize that the winds do not represent a brief episode but a continuous process throughout the Wolf-Rayet phase. Every second, vast amounts of material stream away from the star, and every second the surface composition becomes slightly more exposed. Over tens of thousands of years, this steady erosion reshapes the star completely. By the time it reaches the end of its life, it is no longer the star it once was, but a stripped core prepared for collapse. The winds are therefore not simply observational features, they are central to the destiny of the star. In summary, Wolf-Rayet winds are line-driven outflows of extraordinary power carrying away significant fractions of stellar mass at speeds of thousands of kilometers per second. They are clumpy metallicity dependent and influential, both for the star's evolution and for its environment. Without these winds, the class of Wolf-Rayet stars would not exist because the surface would never be stripped to reveal the nuclear ashes beneath. The winds are the defining mechanism that connects the inner processes of fusion with the outer signature of broad emission lines, making them essential to both the identity and the significance of Wolf-Rayet stars. The strength and character of Wolf-Rayet stellar winds are not uniform across all galaxies. They depend strongly on the chemical composition of the star's environment, which astronomers describe with the term metallicity. In astrophysics, metallicity refers to the abundance of all elements heavier than hydrogen and helium. These elements provide the atomic lines that interact with radiation, allowing photons to transfer momentum and drive winds. The more lines available, the stronger the coupling between light and matter, and the more effective the mass loss becomes. This principle explains why metallicity is one of the most important factors determining how Wolf-Rayet stars evolve and how common they are in different galaxies. In the Milky Way, metallicity is relatively high compared with many nearby dwarf galaxies. As a result, massive stars in our galaxy have strong winds that strip away their hydrogen envelopes efficiently. This allows many of them to evolve into Wolf-Rayet stars within just a few million years of their birth. Surveys suggest that there are at least several hundred Wolf-Rayet stars in the Milky Way, though many are hidden by dust. The relatively high metallicity of the galactic environment ensures that radiation-driven winds are powerful enough to expose fusion products at the surface. In contrast, in the large and small Magellanic Clouds, metallicity is significantly lower. These satellite galaxies of the Milky Way have lower abundances of heavy elements, and their stars therefore have fewer atomic lines available to absorb photons. As a result, their winds are weaker, and only the most massive stars can lose enough material to reach the Wolf-Rayet phase. Observational surveys confirm that Wolf-Rayet stars are less numerous in these galaxies, and their subtype distribution is different. In the small Magellanic Cloud, nitrogen sequence Wolf-Rayet stars dominate, while carbon sequence stars are rare. This is consistent with the idea that weaker winds make it difficult for stars to shed enough mass to expose helium-burning products such as carbon and oxygen. The dependence of Wolf-Rayet populations on metallicity provides an important test of stellar evolution theory. Models predict that at very low metallicity, only the most extreme stars with initial masses well above 50 solar masses will reach the Wolf-Rayet stage through winds alone. If metallicity is close to zero, as it was in the early universe, then radiation-driven winds may be too weak to strip away the envelope. In such cases, the only pathway to Wolf-Rayet-like states would be through binary interactions where mass is removed by gravitational transfer to a companion star. This prediction helps connect present-day observations to the expected behavior of the first generations of stars which formed when the universe contained only hydrogen and helium. The link between metallicity and winds can be measured directly through the relation between line strength and outflow rates. In stars with higher metallicity, spectral lines of ions such as carbon-nitrogen and iron show broader profiles and stronger emission consistent with higher mass loss rates. In stars with lower metallicity, the same lines appear weaker, indicating reduced wind strength. This correlation matches theoretical models, giving astronomers confidence that metallicity is the controlling parameter. The dependence is roughly proportional to metallicity raised to a fractional power, meaning that halving the metallicity does not halve the wind strength, but still produces a significant reduction. Metallicity also influences the relative proportions of Wolf-Rayet subtypes. In the Milky Way, carbon sequence stars are relatively common, because high metallicity allows winds to strip deeply enough to reveal helium-burning products. In the Large Magellanic Cloud with lower metallicity, nitrogen-sequenced stars are more common, while carbon-sequenced stars are fewer. In the Small Magellanic Cloud, which has even lower metallicity, carbon-sequenced stars are very rare, and almost all Wolf-Rayet stars are nitrogen-sequenced. Oxygen-sequenced stars are extremely rare in all environments, but their scarcity is even more pronounced at low metallicity. These population differences serve as evidence that wind strength controls how far the stripping process can progress. The effect of metallicity extends to the eventual fate of these stars. Because winds control how much mass is lost before collapse, metallicity indirectly influences the type of supernova produced. At high metallicity, stars lose more mass, leading to stripped envelope supernovae of type Ib and type Eq. At low metallicity, winds are weaker, and stars may retain more of their hydrogen and helium envelopes, producing different types of explosions or possibly collapsing directly into black holes without a bright supernova. This connection makes metallicity an important parameter in predicting the outcomes of massive stellar evolution across cosmic history. Observational campaigns across different galaxies illustrate these principles. In the local group of galaxies, the number of Wolf-Rayet stars scales roughly, with both the total star formation rate and the metallicity. In high metallicity galaxies like M83, thousands of Wolf-Rayet stars are found, and carbon-sequenced stars are abundant. In lower metallicity galaxies like IC 1613, Wolf-Rayet stars are rare, and nearly all of them are nitrogen sequence. These population statistics confirm the predictions of stellar evolution models and provide a way to test theories of wind physics under different environmental conditions. Metallicity also influences the ionizing power of Wolf-Rayet stars. Because winds remove material from the surface, the stellar core becomes hotter and more compact. At higher metallicity, stronger winds can reveal hotter layers, increasing the production of high-energy ultraviolet photons. These photons ionize surrounding gas, creating bright H2 regions. At lower metallicity, weaker winds delay this exposure and the ionizing radiation is reduced. Thus, the feedback effects of Wolf-Rayet stars on their environments are metallicity dependent. This has implications for the early universe, where the first stars may have been less efficient at ionizing their surroundings, compared with present-day massive stars. Another consequence of metallicity differences is the variation in lifetimes of the Wolf-Rayet phase. At high metallicity, stars enter the Wolf-Rayet phase earlier and spend a longer fraction of their lives in it, because strong winds strip the envelope quickly. At low metallicity, fewer stars reach the phase, and those that do spend less time in it, because stripping is incomplete. This explains why Wolf-Rayet populations in low metallicity galaxies are not only smaller, but also show different distributions of subtypes. The role of metallicity in shaping Wolf-Rayet winds has broader significance for galactic chemical evolution. The material expelled in winds is enriched in nitrogen, carbon, and oxygen. In galaxies with high metallicity, strong winds contribute large amounts of these elements to the interstellar medium, enhancing chemical enrichment. In low metallicity galaxies, weaker winds reduce this contribution, slowing the buildup of heavy elements. Over cosmic time, this feedback influences how galaxies evolve chemically and how new generations of stars form. In summary, metallicity is a key parameter controlling the wind's lifetime subtype distribution and eventual fates of Wolf-Rayet stars. Higher metallicity strengthens winds, accelerates envelope stripping, and increases the frequency of carbon-sequenced stars. Lower metallicity weakens winds, prolongs hydrogen retention, and limits the exposure of deeper fusion products. These differences explain the variations observed in Wolf-Rayet populations across galaxies, and provide insights into how massive stars behaved in the early universe. The metallicity dependence of Wolf-Rayet stars therefore links the physics of individual stellar winds to the chemical and evolutionary history of galaxies. Rotation and magnetic fields play a central role in shaping the behavior of Wolf-Rayet stars, influencing how material is lost, how surfaces are mixed with deeper layers, and how the stars progress toward their final states. While the winds of Wolf-Rayet stars are primarily driven by radiation pressure, the rotation of the star can alter how effectively these winds carry material away. A rapidly rotating star is not the same as a slowly rotating one, even if both begin with similar masses and metallicities. Rotation modifies the balance between gravity and outward forces, and magnetic fields, when present, can redirect flows and trap material. These additional layers of physics complicate but also enrich the understanding of Wolf-Rayet evolution. When a massive star rotates rapidly, centrifugal force acts to reduce the effective gravity at the equator. This makes it easier for material at the equator to escape, enhancing mass loss in that region. The star is no longer a perfect sphere but becomes ablate with an equatorial bulge. Observationally, this can lead to anisotropic winds where mass loss is stronger in some directions than others. Over time, such directional mass loss can alter the angular momentum of the star, slowing its rotation. But before it slows down, rapid rotation has another important effect. It stirs the interior. Rotation induces mixing between the core and the envelope, bringing fusion products closer to the surface. This mixing can cause nitrogen, carbon, and oxygen to appear at the surface earlier than they otherwise would. As a result, a rapidly rotating star may show Wolf-Rayet features sooner in its life than a slowly rotating counterpart. The degree of rotational mixing depends on the initial spin rate of the star. Some massive stars are observed to rotate at a significant fraction of their critical speed, the rate at which centrifugal force at the equator would completely balance gravity. At such high speeds, mixing is efficient and chemical differences between the core and surface are reduced. In extreme cases, rotation can keep the star chemically homogeneous, with the same composition throughout most of its interior. These chemically homogeneous stars evolve differently from ordinary stars, and some of them may bypass the normal Wolf-Rayet sequence, altogether appearing as Wolf-Rayet-like stars throughout much of their short lifetimes. This pathway is thought to be more common at low metallicity, where weaker winds are less effective at slowing rotation. Magnetic fields add further complexity. When a star possesses a strong magnetic field, the field lines can guide the flow of charged particles, channeling winds along specific directions. This can produce structured outflows rather than isotropic winds. In some cases, magnetic fields can trap material in closed loops near the surface, forming magnetospheres where gas is confined before eventually escaping. Observations of certain massive stars suggest that magnetic confinement can influence the variability and geometry of winds. While direct measurements of magnetic fields in Wolf-Rayet stars are difficult, indirect evidence indicates that fields may play a role in at least some cases. The combination of rotation and magnetic fields also affects angular momentum loss. As mass is carried away in winds, it removes angular momentum from the star, gradually slowing its rotation. If magnetic fields are strong, they can couple the wind more effectively to the star's rotation, enhancing angular momentum loss. This process is important for the final collapse of the star. If the star retains too much angular momentum, it may produce a rapidly rotating core, which under certain conditions can give rise to phenomena such as long-duration gamma-ray bursts. If angular momentum is lost efficiently, the core rotation may be too slow to support such events. Thus, understanding the interplay between wind's rotation and magnetic fields is essential for predicting the end stages of Wolf-Rayet stars. Observations of Wolf-Rayet binaries provide additional evidence for the role of rotation. In some close binary systems, tidal forces from the companion can synchronize the rotation of the Wolf-Rayet star with its orbital period. This can either spin up or slow down the star depending on the initial conditions. Tidal interactions may therefore preserve or even enhance rotation in stars that would otherwise lose angular momentum through winds. In such cases, the combination of rapid rotation and mass loss can create unique evolutionary tracks, possibly leading to unusual supernova outcomes or exotic remnants. Rotation also influences how Wolf-Rayet stars distribute their mass loss across time. In rapidly rotating stars, the loss of angular momentum through winds can slow rotation to more moderate values over millions of years. The star's appearance as a Wolf-Rayet object may therefore change as its rotation changes, with mixing more prominent early on and less significant later. This gradual evolution complicates attempts to place stars into neat categories, since their properties are not static, but vary as they shed both mass and angular momentum. Magnetic fields, though harder to measure directly, may also leave signatures in the circumstellar environment. Structured nebulae around some Wolf-Rayet stars show arcs, filaments, or other patterns that could reflect magnetically guided outflows. In colliding wind binaries, shocks that form between the two stars' winds can also be influenced by magnetic fields, altering the shape and intensity of emission in radio and X-ray wavelengths. These indirect clues suggest that magnetic fields, while elusive, cannot be ignored in the physics of Wolf-Rayet stars. Theoretical models attempt to capture the combined effects of rotation, magnetic fields, and winds, but the parameter space is wide. Some models predict that at very low metallicity, rotation plays an outsized role, allowing chemically homogeneous evolution to proceed and producing Wolf-Rayet-like stars even when winds are weak. Other models suggest that strong magnetic coupling can slow rotation enough to prevent such outcomes. Observational tests are ongoing, but the complexity of these systems makes firm conclusions difficult. Despite these uncertainties, the consensus is clear on several points. Rotation enhances internal mixing, allowing fusion products to reach the surface earlier. Rapid rotation can produce chemically homogeneous stars that appear as Wolf-Rayet stars for a significant fraction of their lives. Magnetic fields can shape winds, confine material, and enhance angular momentum loss. Together, rotation and magnetism determine how quickly a star spins down, how its surface composition evolves, and whether it retains enough angular momentum to produce exotic transients at collapse. The story of Wolf-Rayet stars is therefore not complete without considering rotation and magnetic fields. These forces act alongside radiation-driven winds to strip envelopes, expose nuclear ashes, and shape the final states of massive stars. In some cases, they accelerate evolution. In others, they slow it down. They may determine whether the final explosion is a type Ib or type X supernova, or whether the star collapses quietly into a black hole. They may also decide whether a collapsing core produces a jet powerful enough to pierce through the star and create a gamma-ray burst. Each of these outcomes depends not only on mass and metallicity, but also on how the star has spun, how it has mixed, and how its fields have guided its winds over millions of years. In summary, Wolf-Rayet stars are sculpted not only by their immense luminosities and winds, but also by the subtler yet profound effects of rotation and magnetism. Rapid spin mixes the interior and brings nuclear products to the surface. Magnetic fields shape winds and govern angular momentum loss. Their interplay introduces variability, anisotropy, and complexity into the life cycles of these stars. Without considering rotation and magnetic fields, the picture of Wolf-Rayet evolution would be incomplete. With them, the narrative becomes one of dynamic interaction, where forces both visible and hidden shape the fates of the most massive stars in the universe. Wolf-Rayet stars rarely live in isolation. observations across the Milky Way and nearby galaxies consistently show that a large fraction of them are found in binary systems where two massive stars orbit a common center of mass. In such systems, the evolution of each star is not independent but deeply interconnected with winds, radiation, and gravity shaping their shared development. The importance of binarity in massive stars is now widely accepted. Surveys indicate that more than half of all massive stars have close companions, and for Wolf-Rayet stars this fraction is similarly high. Understanding the physics of binaries is therefore essential to understanding Wolf-Rayet stars themselves. When two massive stars are born close together, their mutual gravity influences their evolution from the very beginning. As the more massive star evolves faster, it expands and may fill its Roche lobe, the region around a star where material remains gravitationally bound. Once the star fills this region, gas flows through the inner Lagrange point toward its companion. This process strips the donor star of its outer layers far more efficiently than winds alone producing a Wolf-Rayet star, even if its initial mass is not high enough for wind stripping to succeed. The companion meanwhile accretes material and may grow more massive, altering its own evolutionary path. In some binaries, both stars are massive enough to eventually become Wolf-Rayet stars. Their winds collide at supersonic speeds, producing shocks where kinetic energy is converted into heat and radiation. These shocks create X-ray emission observable with space telescopes, and can also produce non-thermal radio emission through accelerated particles. The collision region takes the form of a curved bow-shaped surface determined by the relative strengths of the two winds. If one wind is stronger, the shock is pushed closer to the weaker star. These colliding wind binaries serve as natural laboratories for studying shock physics under extreme conditions, as well as providing direct measures of wind momentum and density. The interaction of winds in binaries also leads to remarkable dust formation in certain cases. In some Wolf-Rayet binaries, the colliding winds compress gas into dense regions where dust grains can condense, despite the otherwise hostile conditions near such hot stars. As the stars orbit each other, the dust is carried outward by the winds, forming spiral structures known as pinwheel nebulae. These spirals have been imaged in infrared light where the dust glows brightly. They provide striking evidence of how binary interactions can create complex and beautiful circumstellar structures that would not exist around single Wolf-Rayet stars. The presence of a companion also alters angular momentum evolution. Tidal forces can synchronize the spin of the Wolf-Rayet star with its orbital motion, changing how quickly it rotates compared with a single star. In some cases, this tidal locking preserves rapid rotation, allowing the star to retain enough angular momentum in its core to be a candidate for producing a long-duration gamma-ray burst at collapse. In other cases, tidal forces slow rotation, leading to different outcomes. Thus, the orbital configuration plays a direct role in determining the end-of-life events of Wolf-Rayet stars. Binary interactions also affect the timing and type of supernovae. A Wolf-Rayet star formed through binary stripping may retain less mass than one formed by winds alone, and its explosion may therefore be less energetic. Alternatively, if both stars in the binary explode in sequence, the first supernova can influence the environment into which the second one occurs, enriching it with heavy elements or clearing cavities in the interstellar medium. In some systems, the explosion of one star may even unbind the binary, sending the surviving Wolf-Rayet star hurtling through space as a runaway star. Such runaway Wolf-Rayet stars have been observed traveling at high velocities away from their birth clusters. The study of binary Wolf-Rayet systems is advanced by multi-wavelength observations. Optical spectra reveal periodic Doppler shifts as the stars orbit each other, allowing astronomers to measure orbital periods and masses. X-ray telescopes detect the hot plasma produced in colliding winds, while radio observations trace non-thermal emission from accelerated particles. Infrared imaging reveals the dust spirals in systems that produce pinwheel nebulae. Each wavelength probes a different aspect of the binary interaction, and together they provide a complete picture of the physics at work. One famous example of a Wolf-Rayet binary is WR140, a system consisting of a Wolf-Rayet star and an O-type companion. Their highly eccentric orbit brings them close together every few years, at which point their colliding winds produce bursts of dust that expand outward to form concentric shells. These shells observed in infrared reveal the history of dust production over multiple orbital cycles. The system demonstrates how binary interactions can create long-term records of stellar behavior preserved in expanding structures round the stars. Binaries also serve as progenitors for some of the most energetic events in the universe. When two massive stars in a binary both collapse into compact remnants, such as black holes or neutron stars, they may eventually merge, releasing gravitational waves detectable across the cosmos. The formation of such systems often requires at least one star to pass through a Wolf-Rayet phase stripped by binary interaction. Thus, Wolf-Rayet binaries are part of the evolutionary pathway that leads to the mergers now observed by detectors such as LIGO and Virgo. The importance of binaries extends even further. In low metallicity environments where winds are too weak to produce many Wolf-Rayet stars, binary stripping can compensate, creating a significant fraction of the observed Wolf-Rayet population. This makes binarity not just an interesting complication, but a necessary ingredient in explaining the distribution of Wolf-Rayet stars across different galaxies. Without binaries, the number of Wolf-Rayet stars at low metallicity would be too low compared with what is observed. Including binaries in models brings theory and observation into closer alignment. Despite their importance, many questions remain about Wolf-Rayet binaries. The fraction of systems with strong colliding winds, the frequency of dust-producing binaries, and the role of magnetic fields in shaping interactions are still under study. Observations are challenging because these stars are rare and often distant, requiring long monitoring campaigns to detect orbital motions. Nonetheless, the consensus is that binaries are central to understanding both the formation and the final fates of Wolf-Rayet stars. In summary, binary interactions are a key aspect of Wolf-Rayet evolution. They strip envelopes, create shocks, form dust spirals, alter rotation, and shape the outcomes of supernovae and compact object mergers. Colliding wind binaries reveal the physics of shocks and particle acceleration, while dust-producing binaries demonstrate how even in extreme environments complex structures can form. The high fraction of Wolf-Rayet stars found in binaries ensures that any complete picture of these stars must include the gravitational influence of companions. Rather than existing alone, most Wolf-Rayet stars live intertwined lives, their fates linked to those of their partners and their interactions written into the spectra, winds and nebulae that astronomers observe today. Among the many surprising behaviors of Wolf-Rayet stars is their ability under certain circumstances to form dust. This might seem unlikely at first because these stars are extremely hot with surface temperatures of tens of thousands of degrees. Kelvin and their winds are fast, dense, and bathed in intense ultraviolet radiation. Such conditions should destroy dust grains rather than allow them to condense. Yet observations show that dust does exist around some Wolf-Rayet systems, and in rare cases it organizes into striking spiral shapes called pinwheel nebulae. The existence of dust in these environments reveals that even in extreme stellar conditions, processes occur that allow matter to condense, survive, and flow outward in structured patterns. Dust formation in Wolf-Rayet stars almost always requires the presence of a companion. In binaries where a Wolf-Rayet star is paired with a massive O-type star, the collision of their winds creates regions of compressed gas. At the interface where the winds meet, density increases and temperature decreases just enough for dust grains to form. The dust then becomes entrained in the outflow, spiraling outward as the stars orbit each other. Infrared observations reveal this dust, which glows brightly as it absorbs ultraviolet light and re-emits it at longer wavelengths. Systems of this type are relatively rare, but they provide important insights into how matter behaves under conditions of strong radiation and high-speed winds. The Pinwheel nebulae formed in such binaries are among the most visually striking features in stellar astrophysics. Infrared images taken with large telescopes show curved spiral arms of dust extending outward like the blades of a pinwheel toy. Each spiral corresponds to one orbital cycle of the binary system, with dust continuously produced at the collision zone and then carried outward by the winds. As time passes, the spiral unwinds farther from the stars, preserving a record of the orbital motion. The geometry of the spiral provides direct information about the orbital period and the wind velocities, offering astronomers a way to measure properties of the system that would otherwise be difficult to determine. The best-known example of such a system is WR104, a Wolf-Rayet star paired with an O-type companion. Infrared imaging reveals a near-perfect spiral of dust, extending many times the separation of the stars. Each turn of the spiral corresponds to the orbital period of the binary, which is about 240 days. The dust formed at the collision zone is remarkably persistent, surviving despite the hostile radiation environment. WR104 and similar systems demonstrate that dust can form in Wolf-Rayet binaries under the right conditions, and that once formed it can create large-scale structures that persist for years or even centuries. Not all Wolf-Rayet binaries produce dust. The ability to do so depends on several factors, including wind densities, orbital separation, and the balance between radiation heating and cooling. If the winds are too tenuous, compression at the collision zone is insufficient to form dust. If the stars are too far apart, the interaction may be weak. If they are too close, the radiation field may be too strong to allow dust survival. Only systems with the right combination of parameters can produce stable, long-lived dust spirals. These conditions are rare, which is why pinwheel nebulae are not common, despite the relatively high binary fraction among Wolf-Rayet stars. Dust formation is important not only as a curiosity, but also as a contributor to galactic chemical enrichment. The dust grains formed in Wolf-Rayet systems contain carbon and other heavy elements created in the star's interior. As the dust drifts into the interstellar medium, it mixes with gas and becomes part of the raw material for future generations of stars and planets. Wolf-Rayet dust is therefore one pathway by which elements forged in massive stars are incorporated into the broader cycle of matter in galaxies. In some regions, the cumulative contribution of Wolf-Rayet stars may be significant, especially if many such binaries are present in a star-forming cluster. The study of dust formation also helps refine models of stellar winds. The very existence of dust indicates that dense, cool regions must form somewhere within the otherwise hot outflows. This suggests that clumping is not only present but essential. Clumps provide the density enhancements needed for dust nucleation, and the wind-wind collision zones in binaries create precisely these dense regions. Observations of dust spirals therefore support the idea that Wolf-Rayet winds are structured and inhomogeneous rather than smooth and uniform. Infrared monitoring of dust-producing Wolf-Rayet binaries reveals variations in brightness, correlated with orbital motion. In systems with eccentric orbits, dust production peaks near periastron, the point of closest approach when the colliding winds are most intense. This produces periodic infrared brightening, which can be used to measure orbital properties. In some systems, repeated episodes of dust production over decades create concentric shells visible in high-resolution images. These shells serve as fossil records of past interactions, much like tree rings, preserve the growth history of a tree. Pinwheel nebulae are not the only circumstellar structures associated with Wolf-Rayet dust. Some systems show more irregular dust clouds, arcs, or filaments, depending on wind geometry and orbital inclination. These variations demonstrate the diversity of outcomes even within the subset of dust-producing Wolf-Rayet binaries. Each system provides a unique laboratory for studying how dust forms and survives in hostile conditions. The role of dust extends to the eventual explosion of these stars as supernovae. Dust around a Wolf-Rayet star can obscure the progenitor, making it harder to detect before the explosion. After the explosion, interaction between the supernova shock and the surrounding dust can produce infrared echoes or unusual light curve features. Thus, dust influences both pre-explosion observations and post-explosion behavior. Understanding dust around Wolf-Rayet stars is therefore essential for interpreting supernova data as well. Dust-producing Wolf-Rayet binaries also have implications for long-duration gamma-ray bursts. If such a star were to collapse while surrounded by a dusty spiral, the interaction between the relativistic jet and the dust could alter the observable properties of the burst. While this remains a topic of ongoing research, it illustrates how the presence of dust can influence not only stellar evolution, but also the appearance of the most energetic explosions in the universe. In summary, dust formation in Wolf-Rayet stars highlights the interplay between winds, binarity, and chemistry. While individual Wolf-Rayet stars are too hot to allow dust to form in their winds, binary interactions create dense shielded regions where dust can condense. The resulting spirals, shells, and clouds are visible in infrared light and provide direct records of orbital motion and wind properties. These structures enrich the interstellar medium with heavy elements and influence both the evolution of the stars and the interpretation of their eventual explosions. Dust around Wolf-Rayet stars is therefore not an anomaly, but a window into the complex processes that govern the lives of the most massive stars. Wolf-Rayet stars are not passive objects in their surroundings. Their intense radiation and their fast, dense winds exert powerful feedback on the interstellar medium, shaping the gas and dust nearby. This feedback comes in two main forms: ionizing radiation that alters the state of surrounding gas and mechanical energy from the winds that pushes and compresses that gas. Together, these influences create H2 regions, cavities and shells that can extend many light years from the star. The effects of this feedback are visible across the electromagnetic spectrum and play an important role in regulating star formation and enriching galaxies with heavy elements. The radiation emitted by a Wolf-Rayet star is dominated by ultraviolet photons, many of which are energetic enough to ionize hydrogen. When such photons encounter a cloud of neutral hydrogen, they strip electrons from the atoms, creating a region of ionized gas called an H2 region. These regions are visible in optical wavelengths as glowing nebulae, where recombination of electrons with protons produces emission lines such as hydrogen alpha. Because Wolf-Rayet stars are so hot with surface temperatures, often above 50,000 degrees Kelvin, they produce enormous quantities of ionizing photons. A single Wolf-Rayet star can create an H2 region, extending tens of light years in radius, influencing not only its immediate surroundings, but also the larger structure of the interstellar medium. The winds of Wolf-Rayet stars add a mechanical component to this feedback. As matter flows outward at thousands of kilometers per second, it collides with surrounding gas and sweeps it up into expanding shells. The energy carried by these winds is immense, and when it is deposited into the surrounding medium, it can carve out cavities known as wind-blown bubbles. These bubbles are observed around many Wolf-Rayet stars, sometimes as spherical shells, sometimes as irregular arcs or filaments depending on the density distribution of the surrounding gas. The swept-up shells can themselves become sites of new star formation if the compression triggers the collapse of dense clumps within them. The combined action of radiation and winds produces complex structures. In some cases, the ionizing radiation creates a large bubble of hot, low-density plasma, while the winds sweep up a dense shell at the bubble's edge. Infrared observations show the warm dust in these shells, while optical images reveal emission lines from ionized gas. Radio observations detect free emission from electrons in the ionized regions, and X-ray observations sometimes reveal the hot shocked gas inside the bubble. Multi-wavelength studies are therefore essential to capture the full picture of Wolf-Rayet feedback. One striking example of this interaction is the Nebula NGC 6E88, also known as the Crescent Nebula, which surrounds the Wolf-Rayet star WR136. This nebula consists of material shed by the star in earlier evolutionary stages swept up and ionized by the present-day winds and radiation. The Crescent Nebula displays arcs and filaments that trace the dynamics of wind interaction with surrounding gas. Its emission lines reveal enrichment in nitrogen and helium, confirming that the material originated in the star's interior and was expelled during mass loss. This object illustrates how Wolf-Rayet feedback both shapes the interstellar medium and provides direct evidence of stellar evolution. Feedback from Wolf-Rayet stars has implications for the broader process of star formation in galaxies. By ionizing and dispersing gas, these stars can inhibit further star formation in their immediate vicinity, preventing molecular clouds from collapsing. At the same time, the compression of shells by winds can trigger star formation at the edges of bubbles. This dual role of feedback, sometimes suppressing, sometimes enhancing star formation, makes Wolf-Rayet stars important regulators of galactic evolution. The net effect depends on the balance between dispersal and compression, which varies from region to region. The chemical enrichment provided by Wolf-Rayet winds is also significant. Because these stars have lost their hydrogen envelopes, their winds carry out products of nuclear fusion, including nitrogen, carbon, and oxygen. These elements are injected into the interstellar medium where they mix with surrounding gas. Over time, they contribute to the chemical enrichment of galaxies, raising the abundance of heavy elements available for new generations of stars and planets. Observations of Wolf-Rayet nebulae confirm this enrichment, showing elevated levels of nitrogen compared with surrounding gas. The winds of carbon-sequence Wolf-Rayet stars contribute carbon and oxygen as well, adding to the variety of enrichment. The influence of Wolf-Rayet stars can extend beyond their immediate regions. In massive star-forming complexes, groups of O-type and Wolf-Rayet stars collectively produce vast H2 regions and superbubbles. These structures, sometimes spanning hundreds of light-years, are shaped by the combined radiation and winds of many massive stars. They play a central role in the life cycle of gas in galaxies, dispersing molecular clouds, injecting energy into the interstellar medium, and driving turbulence that regulates future star formation. Wolf-Rayet stars, being among the most energetic, are key contributors to these collective effects. Feedback from Wolf-Rayet stars is not only mechanical and radiative, but also dynamical. As winds interact with surrounding gas, they can create instabilities that lead to complex filamentary structures. These structures are observed in optical and infrared images of Wolf-Rayet nebulae, where arcs and knots reveal the turbulent interface between winds and ambient material. The dynamics of these interactions provide insights into fluid instabilities and shock physics under astrophysical conditions. The importance of Wolf-Rayet feedback is underscored by its role in preparing the environment for supernova explosions. When a Wolf-Rayet star eventually collapses, the shock wave from the explosion expands into a medium that has already been shaped by winds and radiation. The density distribution composition and structure of this medium determine how the supernova appears, how its light curve evolves, and how efficiently it produces observable phenomena such as gamma-ray bursts. Thus, the pre-supernova feedback of Wolf-Rayet stars sets the stage for the final events of their lives. Despite extensive observations, uncertainties remain about the efficiency of feedback. Measuring the total energy injected into the interstellar medium requires combining data from many wavelengths and modeling the geometry of the interactions. Clumping in winds, asymmetries in radiation fields, and variations in ambient density all complicate the picture. Nonetheless, the consensus is that Wolf-Rayet stars are major sources of feedback in star-forming regions and significant contributors to galactic chemical and dynamical evolution. In summary, Wolf-Rayet stars influence their surroundings through both ionizing radiation and powerful winds. They create H2 regions, carve bubbles, sweep up shells, and enrich the interstellar medium with processed material. Their feedback regulates star formation, sometimes suppressing it by dispersing clouds, sometimes triggering it by compressing gas. Their winds prepare the environment for future supernovae, shaping how those explosions unfold. Observations of nebulae like the Crescent Nebula confirm these processes and provide direct evidence of nuclear enrichment. Wolf-Rayet feedback is therefore a fundamental part of how galaxies evolve, linking the lives of individual stars to the broader cycles of gas radiation and star formation across cosmic time. Studying Wolf-Rayet stars requires the use of many different observational techniques because no single wavelength of light can provide all the necessary information about their structure, composition, and winds. These stars are complex systems with surfaces hotter than 50,000 degrees Kelvin, dense outflows moving at thousands of kilometers per second, and circumstellar environments that include shocks, clumps, and sometimes dust. Each part of the electromagnetic spectrum offers a different diagnostic window into these phenomena. By combining observations in ultraviolet, optical, infrared, radio, and X-ray light, astronomers build a more complete picture of what Wolf-Rayet stars are and how they behave. Ultraviolet observations are particularly important for Wolf-Rayet stars because many of the strongest resonance lines of carbon, nitrogen, oxygen, and helium occur at ultraviolet wavelengths. Instruments on space telescopes above Earth's atmosphere can detect these lines in detail. Ultraviolet spectra reveal the ionization states of different elements and the velocities of outflows through line profiles. Features known as P Cygni profiles, which consist of blue-shifted absorption and red-shifted emission, are clear indicators of expanding winds. These profiles allow astronomers to measure terminal wind speeds of up to 3,000 km per second. Ultraviolet data also reveal the presence of highly ionized species that cannot be detected in the optical, providing essential information about the hottest regions of the wind. Optical spectroscopy has historically been the defining tool for identifying Wolf-Rayet stars. Their broad emission lines of helium, nitrogen, carbon, or oxygen are most easily seen at visible wavelengths. Optical data remain essential for classification into nitrogen sequence, carbon sequence, and oxygen sequence types, and for assigning numerical subtypes based on line strengths and ratios. Long-term optical monitoring also reveals variability in line intensities, which can indicate changes in wind density or the presence of clumps. In binary systems, periodic shifts in line wavelengths provide orbital parameters, allowing astronomers to measure the masses of the stars. Optical imaging combined with spectroscopy can also capture the appearance of surrounding nebulae created by past mass loss. Infrared observations extend this picture by penetrating dust that obscures many Wolf-Rayet stars in the Milky Way. Because dust absorbs visible light but re-emits in the infrared, dusty Wolf-Rayet systems often appear bright at long wavelengths. Infrared imaging has revealed the Pinwheel nebulae formed in colliding wind binaries, where spirals of dust extend outward over large distances. Infrared spectroscopy detects molecular features such as carbon-rich dust signatures that cannot be studied in other bands. Large infrared surveys have been instrumental in identifying new Wolf-Rayet stars hidden behind interstellar dust, increasing the known population in our galaxy. These observations are especially valuable for population studies since many Wolf-Rayet stars would otherwise remain undiscovered. Radio observations probe the ionized gas in Wolf-Rayet winds. Free emission from electrons moving in the electric fields of ions produces a continuous radio signal whose intensity depends on the density of the ionized gas. By measuring this radio flux, astronomers can estimate mass loss rates independently of optical or ultraviolet methods. Radio observations are also sensitive to non-thermal emission from particles accelerated in colliding wind binaries. When two winds collide, shocks can accelerate electrons to relativistic speeds, producing synchrotron radiation in the radio band. Detection of such emission provides evidence for particle acceleration processes similar to those that occur in supernova remnants, but in a steady-state stellar context. X-ray observations add another layer of diagnostics. While single Wolf-Rayet stars are generally weak, X-ray sources, binaries with colliding winds, can produce significant X-ray emission from hot-shocked gas. The temperature of this gas can reach tens of millions of degrees, Kelvin, producing X-rays detectable with modern satellites. The X-ray spectrum reveals details of the shock temperature density and cooling processes, offering constraints on wind properties and collision dynamics. X-ray variability correlated with orbital phase provides further information about the geometry of colliding winds. In some systems, eclipses by one star can modulate the observed X-rays, giving clues to the distribution of hot plasma. Each observational method has limitations, which is why multi-wavelength approaches are essential. Ultraviolet data are limited to space-based instruments which have restricted observing time. Optical spectra can be contaminated by interstellar absorption or by surrounding nebulae. Infrared observations require sensitive detectors and can be affected by background emission from interstellar dust. Radio measurements need long integration times to detect faint free emission. X-ray data are sensitive but limited by the faintness of many Wolf-Rayet sources. By combining all these approaches, astronomers can cross-check results and build a coherent picture that compensates for individual weaknesses. Examples of such combined studies demonstrate the power of multi-wavelength observations. For instance, the Wolf-Rayet binary WR140 has been studied in optical light to determine its orbit in infrared, to image its dust spirals in radio, to detect synchrotron emission from colliding winds, and in X-rays to study shock-heated plasma. Each wavelength reveals a different facet of the system, and only by combining them does the full complexity emerge. This approach is now standard in Wolf-Rayet research, where progress depends on integrating diverse data sets into unified models. In addition to electromagnetic observations, future studies may also include neutrinos and gravitational waves. Although Wolf-Rayet stars are not currently known as strong neutrino or gravitational wave sources, their explosions as supernovae and their role in binary compact object mergers make them relevant for these fields. Observations in these new windows will complement traditional techniques and may one day reveal additional aspects of Wolf-Rayet physics. Spectroscopic surveys across nearby galaxies also rely on these methods. Optical and infrared surveys identify Wolf-Rayet candidates by their emission line features, while follow-up observations in ultraviolet and radio refine their classifications. Population studies then compare the numbers and types of Wolf-Rayet stars across environments of different metallicities, testing theories of stellar evolution. These surveys are ongoing with both ground-based telescopes and space missions, and they continue to expand the catalogue of known Wolf-Rayet stars. Advances in instrumentation are continually improving observational capabilities. The Hubble Space Telescope has provided high-resolution ultraviolet spectra. The James Webb Space Telescope now offers unprecedented sensitivity in the infrared, capable of detecting faint dust spirals and revealing chemical compositions of circumstellar material. Large ground-based observatories equipped with multi-object spectrographs allow efficient surveys of entire star-forming regions, identifying Wolf-Rayet stars in large numbers. X-ray satellites such as Chandra and XMM Newton have provided detailed spectra of colliding wind binaries. Each technological advance extends the reach of observations and refines the understanding of these stars. In summary, the study of Wolf-Rayet stars depends on a suite of observational methods spanning the electromagnetic spectrum. Ultraviolet data reveal ionization and wind speeds. Optical spectra provide classification and variability. Infrared observations detect dust and penetrate obscured regions. Radio measurements give independent mass loss rates, and X-rays probe colliding winds and shocks. Together, these techniques create a comprehensive portrait of Wolf-Rayet stars, capturing both their surfaces and their surroundings. Without this multi-wavelength approach, the complexity of these stars would remain hidden. With it, astronomers can piece together the intricate interplay of radiation winds and nuclear processes that define the Wolf-Rayet phenomenon. Wolf-Rayet stars are found not only in the Milky Way but also in many nearby galaxies, and their distribution across different environments provides crucial information about how massive stars evolve. Population studies aim to determine how many Wolf-Rayet stars exist in a given galaxy, how they are divided among nitrogen sequence, carbon sequence, and oxygen sequence types, and how these proportions vary with metallicity, star formation rate, and environment. By comparing populations across galaxies, astronomers test theories of stellar evolution and wind physics under conditions that cannot be replicated in laboratories. One of the best studied environments for Wolf-Rayet populations is the Large Magellanic Cloud, a satellite galaxy of the Milky Way with metallicity lower than that of our galaxy. Surveys of this galaxy have identified more than 100 Wolf-Rayet stars, with the majority being nitrogen sequence types. Carbon sequence stars are less common, and oxygen sequence stars are extremely rare. This distribution matches theoretical expectations, with lower metallicity winds are weaker, so stars have greater difficulty shedding enough mass to expose helium-burning products such as carbon and oxygen. As a result, many stars stall at the nitrogen sequence stage rather than progressing further. The Small Magellanic Cloud, with metallicity even lower than that of the Large Magellanic Cloud, has an even more striking population imbalance. Fewer than 20 Wolf-Rayet stars have been identified, and nearly all of them are nitrogen sequence stars. The scarcity of carbon sequence stars in this environment strongly supports the idea that metallicity directly controls wind efficiency. In such an environment, only the most massive stars, or those in binary systems where companions assist in stripping, can reach the Wolf-Rayet phase. The rarity of these stars in the Small Magellanic Cloud illustrates how the early universe, with metallicity close to zero, may have produced far fewer Wolf-Rayet stars than galaxies do today. In contrast, galaxies with higher metallicity, such as M83, show a very different pattern. In M83, a spiral galaxy with metallicity higher than that of the Milky Way surveys have revealed thousands of Wolf-Rayet stars. Among these, carbon sequence stars are relatively abundant because the higher metallicity leads to stronger winds that strip envelopes more efficiently. The large population of Wolf-Rayet stars in such galaxies demonstrates how metallicity boosts the frequency of these stars and alters their subtype distribution. Population statistics across galaxies of different metallicities therefore provide strong observational support for the theoretical prediction that metallicity is the dominant factor governing Wolf-Rayet winds and evolution. To identify Wolf-Rayet populations, astronomers often rely on narrow-band imaging techniques. Filters centered on emission lines such as helium or carbon can reveal Wolf-Rayet candidates by their excess brightness at those wavelengths compared with surrounding continuum. Follow-up spectroscopy then confirms the classification and subtype. This method has been applied to the Magellanic Clouds M33, M83 and many other galaxies steadily building catalogues of Wolf-Rayet stars in environments beyond the Milky Way. The technique is efficient for identifying large numbers of candidates in star-forming regions, which are the natural habitats of massive stars. Population studies also investigate the spatial distribution of Wolf-Rayet stars within galaxies. In the Milky Way and other spirals, they are concentrated in regions of active star formation, often near clusters of O-type stars. This reflects their short lifetimes since they do not live long enough to travel far from their birthplaces. In the Magellanic Clouds, most Wolf-Rayet stars are found in giant H2 regions such as 30 Doradus, where massive star formation is ongoing. The clustering of Wolf-Rayet stars in such regions demonstrates the link between their formation and the densest, most active star-forming environments. The numbers of Wolf-Rayet stars relative to O-type stars also provide tests of stellar evolution models. In the Milky Way, the ratio of Wolf-Rayet stars to O-type stars is higher than in the Magellanic Clouds, consistent with the idea that higher metallicity promotes stronger winds and more Wolf-Rayet formation. In extremely metal-rich galaxies like M83, the ratio is even higher. These ratios are sensitive not only to metallicity, but also to assumptions about binary fractions and mass loss rates. Comparing observed ratios with model predictions allows astronomers to refine parameters such as wind clumping factors and binary interaction frequencies. Population studies extend beyond counting stars to examining their impact on galactic environments. Wolf-Rayet stars contribute large amounts of ionizing radiation and mechanical energy, and in aggregate they influence the structure of H2 regions and superbubbles. In starburst galaxies with high star formation rates, the combined feedback from thousands of Wolf-Rayet stars can dominate the dynamics of the interstellar medium. Spectra of these galaxies often show the broad emission features of Wolf-Rayet stars blended together, creating what astronomers call Wolf-Rayet bumps in the integrated light. These features are used as diagnostics for identifying young, massive stellar populations in distant galaxies where individual stars cannot be resolved. The detection of Wolf-Rayet features in the spectra of distant galaxies provides evidence that massive star formation is occurring there. By comparing the strength of these features with models, astronomers can estimate the number of Wolf-Rayet stars in the population and thus constrain the star formation history. This method has been applied to galaxies observed at high redshift, revealing that Wolf-Rayet stars contribute significantly to feedback even in galaxies billions of light-years away. Such observations connect local studies of individual stars to the broader context of cosmic star formation. Despite these successes, population studies face challenges. Dust extinction can hide Wolf-Rayet stars, particularly in the Milky Way, where much of the galactic plane is obscured. In external galaxies, crowding in dense star-forming regions makes it difficult to isolate individual stars. Spectroscopic confirmation requires large telescopes and significant observing time. Nevertheless, advances in infrared detectors, multi-object spectrographs, and space-based observatories continue to improve the completeness of Wolf-Rayet surveys. The importance of population studies lies in their ability to test theoretical models under diverse conditions. By comparing Wolf-Rayet populations across galaxies of different metallicities, star formation rates and environments, astronomers can refine predictions of wind physics, binary evolution, and supernova progenitors. The variations observed between the Milky Way, the Magellanic Clouds, and metal-rich spirals like M83 provide strong confirmation that metallicity and binarity are the primary factors shaping Wolf-Rayet evolution. In summary, Wolf-Rayet population studies show that these stars are relatively numerous in high metallicity galaxies, rare in low metallicity galaxies, and distributed mainly in star-forming regions close to their birthplaces. This subtype distribution reflects metallicity, with nitrogen sequence stars dominating at low metallicity, and carbon sequence stars more common at high metallicity. Population ratios provide tests of stellar evolution models, while integrated spectral features extend the study of Wolf-Rayet stars to distant galaxies. Through these surveys, astronomers connect the detailed physics of individual stars to the global processes of galactic evolution and cosmic star formation. The fate of Wolf-Rayet stars is closely tied to the violent explosions known as stripped envelope supernovae. These events are classified according to which elements appear in their spectra. Type Ib supernovae lack hydrogen lines but display helium, while type Ic supernovae lack both hydrogen and helium. The defining characteristic of Wolf-Rayet stars is the absence of hydrogen at their surfaces, and in many cases also the absence of helium, depending on how far envelope stripping has progressed. This direct correspondence between surface composition and supernova classification makes Wolf-Rayet stars prime candidates as progenitors of type Ib and type Ic supernovae. The connection is supported by both theory and observation. Models of massive star evolution predict that once a star has lost its hydrogen envelope, either through winds or binary interaction, its collapse will lead to a supernova spectrum without hydrogen. If the helium layer remains intact, the supernova will show helium lines and be classified as type Ib. If both hydrogen and helium are gone, the explosion will lack both and be classified as type Ic. Wolf-Rayet stars with surfaces rich in nitrogen, carbon or oxygen, and depleted in hydrogen and helium match these requirements. Observational evidence also points toward this connection. Supernova surveys have shown that type Ib and type Ic events occur predominantly in star-forming galaxies where massive stars like Wolf-Rayet stars are common. This spatial distribution of these supernovae is concentrated near regions of active star formation, matching the short lifetimes of Wolf-Rayet progenitors. In a few cases, pre-explosion images of supernova sites have been examined, and the absence of a visible progenitor consistent with a red supergiant supports the idea that the progenitor was instead a hot, luminous Wolf-Rayet star hidden by dust or too faint in optical wavelengths. Despite these links, direct confirmation of individual Wolf-Rayet progenitors remains elusive. The rarity of nearby supernovae and the difficulty of detecting hot compact stars in crowded star-forming regions make it challenging to identify progenitors unambiguously. In most cases, the progenitor is invisible in archival images, leaving only indirect evidence. This uncertainty has led to debates about whether all type Ib and type Ic supernovae come from Wolf-Rayet stars, or whether some originate from lower mass stars stripped in binaries. The consensus is that both channels likely contribute, with single Wolf-Rayet stars dominating at high metallicity, where winds are strong, and binary strip stars contributing at lower metallicity. The explosion mechanism itself is influenced by the stripped structure of the progenitor. Without extended hydrogen envelopes, the stars are more compact at collapse, which affects how the shockwave propagates. Compact progenitors produce faster light curves with more rapid rises and declines in brightness than hydrogen-rich supernovae. Observations confirm that type Ib and type Ic supernovae have shorter and fainter light curves than type II supernovae, consistent with the compact structure expected of Wolf-Rayet progenitors. The lack of hydrogen in the spectra also matches the surface composition seen in Wolf-Rayet stars. Another connection is found in nucleosynthesis. Type Ib and type Ic supernovae often show strong oxygen emission in their late-time spectra. This indicates that large amounts of oxygen produced by helium and carbon burning are ejected during the explosion. Wolf-Rayet stars, especially carbon sequence and oxygen sequence stars, have surfaces rich in these elements, suggesting that their cores are correspondingly enriched. The agreement between observed oxygen masses in supernova remnants and predictions from Wolf-Rayet models strengthens the link between the two. There are, however, complexities. Some Type X supernovae are unusually energetic and produce broad absorption features in their spectra, earning the label broad-lined Type X supernovae. These events are thought to be associated with long-duration gamma-ray bursts under certain conditions. Not all broad-lined Type X supernovae show evidence of gamma-ray bursts, but their energy suggests a more extreme collapse mechanism, possibly involving rapidly rotating Wolf-Rayet progenitors with retained angular momentum. The connection between Wolf-Rayet stars and gamma-ray bursts remains an active area of research. Binary interactions complicate the picture further. A Wolf-Rayet star formed through binary stripping may have lower mass at collapse than one formed through winds, and this may influence whether the star explodes as a visible supernova or collapses quietly into a black hole. Some models suggest that the most massive Wolf-Rayet stars may fail to explode, instead collapsing directly into black holes with little or no optical display. Observationally, the apparent absence of very massive progenitors for known Type Ib and Type Ek supernovae supports this idea. If true, it means that not all Wolf-Rayet stars will produce luminous explosions, and that some may die in silence detectable only through the gravitational waves or neutrinos from core collapse. Studies of host galaxies also shed light on progenitor scenarios. Type Ib and Type Ik supernovae are more common in galaxies with higher metallicity, consistent with the expectation that stronger winds at high metallicity create more Wolf-Rayet stars. At lower metallicity, where winds are weaker, these supernovae are rarer, and binary interactions likely play a greater role. This environmental dependence supports the dual-channel model, with both single Wolf-Rayet stars and binary strip stars contributing in different proportions depending on metallicity. The light curves and spectra of individual supernovae provide additional constraints. Detailed modelling of Type Ib and Type Ik explosions allows estimates of progenitor masses, radii, and compositions. In many cases, the inferred progenitor masses are in the range expected for Wolf-Rayet stars, though in others they are somewhat lower, pointing to binary origins. Continued accumulation of well-observed supernovae is gradually refining the statistics, helping to clarify the balance between different progenitor channels. In addition to their role in producing Type Ib and Type Ik supernovae, Wolf-Rayet stars may also be connected to rare transients such as superluminous supernovae and gamma-ray bursts. In particular, long-duration gamma-ray bursts are thought to arise from rapidly rotating Wolf-Rayet stars at low metallicity where angular momentum is preserved. These events, though rare, link the extreme physics of Wolf-Rayet stars to some of the most energetic explosions in the universe. The consensus view is that only a small fraction of Wolf-Rayet stars produce such events, requiring special conditions of rotation, mass, and environment. In summary, Wolf-Rayet stars are widely regarded as the most likely progenitors of Type Ib and Type Ik supernovae. Their stripped surfaces match the spectral properties of these explosions, their locations in galaxies match the distribution of events, and their nucleosynthetic yields match observed abundances, while uncertainties remain about the exact fraction that explode visibly versus collapse silently, and about the relative contributions of single versus binary progenitors. The connection is one of the strongest links between stellar evolution theory and observed transients. Wolf-Rayet stars therefore provide the bridge between massive stellar life and the violent deaths that enrich galaxies and shape the interstellar medium. The possibility that some Wolf-Rayet stars are linked to long-duration gamma-ray bursts has made them subjects of intense study, because these bursts are among the most energetic explosions known. A gamma-ray burst of long duration typically lasts more than 2 seconds, and can release in that short time as much energy as the Sun will emit over its entire lifetime. Observations show that many long gamma-ray bursts are associated with Type X supernovae, especially those with broad spectral lines indicating high expansion velocities. Since carbon sequence and oxygen sequence Wolf-Rayet stars are considered the main progenitors of Type X explosions, it is natural to ask whether they are also the progenitors of some gamma-ray bursts. The leading model for long gamma-ray bursts is the collapsar scenario. In this model, the core of a massive star collapses to form a black hole. If the star retains enough angular momentum, an accretion disk forms around the black hole, and jets of material are launched along the rotational axis. These jets tunnel through the star and escape into space, producing the observed gamma-ray emission. For this mechanism to work, the progenitor star must meet several conditions. It must be stripped of its hydrogen envelope so that the jets are not smothered. It must be compact to allow the jets to escape within the duration of the burst, and it must retain rapid rotation to sustain the disk and power the jets. Wolf-Rayet stars meet the first two conditions naturally, but the third is more difficult because their strong winds usually remove angular momentum along with mass. This is where metallicity becomes important once again. At low metallicity, winds are weaker, and Wolf-Rayet stars may retain more angular momentum until collapse. This allows the collapsar mechanism to operate more effectively. Observations of long gamma-ray bursts support this prediction. They are found preferentially in galaxies with low metallicity, often dwarf irregulars with active star formation. This distribution suggests that only in such environments can Wolf-Rayet progenitors preserve the rapid rotation required for a collapsar. The link between low metallicity Wolf-Rayet stars and long gamma-ray bursts is therefore a key element of the current consensus. Not all Wolf-Rayet stars at low metallicity will produce gamma-ray bursts. Additional factors such as binarity rotation rate and magnetic fields must align in rare ways. For example, in a close binary system, tidal interactions can maintain or even enhance rotation, helping the star retain angular momentum until collapse. Alternatively, mergers between massive stars may spin up the core and provide the conditions for a gamma-ray burst. These special circumstances explain why gamma-ray bursts are rare compared with ordinary type Ib and type Ik supernovae. They represent a small fraction of all Wolf-Rayet deaths, requiring not only the stripped structure, but also the preserved angular momentum needed to launch relativistic jets. The association between long gamma-ray bursts and type Ik supernovae has been confirmed in several well-observed cases. For example, GRB 9804225 was associated with supernova 1998b, a broad-lined type Ik explosion. GRB 030329 was linked to supernova 2003, another broad-line type IC. In both cases, the spectra of the supernova and the properties of the bursts matched predictions from collapsar models. The connection is now considered robust, while not all type Ik supernovae produce gamma-ray bursts. Many gamma-ray bursts are accompanied by type X explosions consistent with Wolf-Rayet progenitors. The role of rotation is central to this picture. A Wolf-Rayet star that rotates slowly at collapse is unlikely to produce a gamma-ray burst, even if it produces a type X supernova. Only if the core retains a rapid spin can an accretion disk form and power jets. The challenge for models is to explain how a Wolf-Rayet star can lose so much mass through winds and still preserve angular momentum. Proposed solutions include chemically homogeneous evolution in rapidly rotating stars where mixing prevents the buildup of a distinct core and envelope. In such stars, winds may remove mass without removing as much angular momentum, allowing rapid rotation to persist. This pathway is thought to be especially important at low metallicity where winds are weaker. Observationally, gamma-ray bursts provide indirect evidence of their progenitors through the afterglow, the fading emission at X-ray, optical and radio wavelengths following the burst. Afterglow modelling often indicates that the environment around the burst is shaped by a stellar wind consistent with a Wolf-Rayet progenitor. The density profiles inferred from afterglows match those expected from winds, with mass loss rates similar to those of Wolf-Rayet stars. This environmental evidence strengthens the link between Wolf-Rayet progenitors and gamma-ray bursts. Another piece of evidence comes from host galaxy studies. Long gamma-ray bursts are found in galaxies with high rates of massive star formation, further supporting their connection to massive stars. They are also often located near the brightest regions of their hosts, consistent with the very short lifetimes of Wolf-Rayet progenitors. The metallicity of these galaxies is typically lower than that of the Milky Way, matching the prediction that low metallicity favors gamma-ray burst production. Together, these observations provide a coherent picture linking Wolf-Rayet stars to gamma-ray bursts under specific conditions. It is important to emphasize that the link between Wolf-Rayet stars and gamma-ray bursts is not absolute. Some gamma-ray bursts may have alternative progenitors such as massive star mergers or exotic channels. Conversely, many Wolf-Rayet stars die without producing gamma-ray bursts. The consensus view is that Wolf-Rayet stars are necessary but not sufficient conditions. They provide the stripped and compact structure required, but only rare subsets with the right rotation and environment go on to produce bursts. The connection has implications beyond stellar evolution. Gamma-ray bursts are so luminous that they can be detected at cosmological distances, serving as beacons of star formation in the early universe. If Wolf-Rayet stars are their progenitors, then studying bursts provides indirect information about the behavior of massive stars at epochs too distant to observe directly. In this way, Wolf-Rayet stars, through their rare but powerful deaths, become tools for probing the distant universe. Despite progress, uncertainties remain. The exact fraction of type Iki supernovae that produce gamma-ray bursts is still debated. The role of magnetic fields in jet formation is not fully understood. Whether chemically homogeneous evolution is common enough to explain observed burst rates is an open question. Future observations with improved sensitivity in both electromagnetic and gravitational wave domains may help resolve these issues. In particular, detecting gravitational waves from collapsar-like events or neutrinos from Wolf-Rayet core collapse would provide decisive tests. In summary, Wolf-Rayet stars are considered the leading progenitors of long-duration gamma-ray bursts, provided they meet the rare conditions of low metallicity, rapid rotation, and stripped envelopes. Their compactness and lack of hydrogen allow jets to escape, while their winds create environments consistent with afterglow observations. The confirmed association of gamma-ray bursts with broad-lined type X supernovae reinforces this link. While not all Wolf-Rayet stars produce bursts, and not all bursts come from Wolf-Rayet stars, the overlap is strong enough to establish a consensus connection. Through this link, Wolf-Rayet stars are not only progenitors of supernovae, but also of some of the most extreme explosions ever observed, connecting the physics of stellar interiors to phenomena visible across the universe.